But now it's starting to be like, well, we can't build that data center because we can't get the energy to it that we need to do the things we want to do with it, because we haven't taken that incremental cost into account over time. We just kind of ignored it. And now we hit like the barrier, right?
Hello, and welcome to Environment Variables, brought to you by the Green Software Foundation. In each episode, we discuss the latest news and events surrounding green software. On our show, you can expect candid conversations with top experts in their field who have a passion for how to reduce the greenhouse gas emissions of software. I'm your host, Chris Adams. Welcome to Environment Variables, where we bring you the latest news and updates from the world of sustainable software development. I'm your host, Chris Adams. If you follow a strict media diet, you switch off the Wi-Fi on your house, and you throw your phone into the ocean, you might be able to avoid the constant stream of stories about AI in the tech industry. For the rest of us, though, it's basically unavoidable. So having an understanding of the environmental impact of AI is increasingly important if you want to be a responsible practitioner navigating the world of AI, generative AI, machine learning models, DeepSeek, and the rest. Earlier this year, I had a paper shared with me with the intriguing title, A Beginner's Guide to Power and Energy Measurement and Estimation for Computing and Machine Learning. And it turned out to be one of the most useful resources I've since come across for making sense of the environmental footprint of AI. So I was over the moon when I found out that two of the authors were both willing and able to come on to discuss this subject today. So joining me today are Dawn Nafus and Charles Tripp, who worked on the paper and did all this research. And well, instead of me introducing them, well, they're right here. I might as well let them do the honors themselves, actually. So I'm just going to work in alphabetical order. Charles, I think you're slightly ahead of Dawn. So can I just give you the room to introduce yourself?
Sure. I'm a machine learning researcher and algorithms researcher. And I've been programming pretty much my whole life since I was a little kid. And I love computers. I researched machine learning and reinforcement learning in particular at Stanford. Started my own company, but kind of got burnt out on it. And then I went to the National Renewable Energy Lab, where I applied machine learning techniques to energy efficiency and renewable energy problems there. And while I was there, I started to realize that computing energy efficiency was an increasingly important area of study on its own. So I had the opportunity to sort of lead an effort there to create a program of research around that topic. And it was through that work that I started working on this paper, made these connections with Dawn. And I worked there for 6 years and just recently changed jobs to be a machine learning engineer at Zazzle.
Okay.
But I'm continuing to do this research. And yeah.
Brilliant. Thank you, Charles. Okay, so national, that's NREL that some people refer to, right?
That's right. It's one of the national labs.
Okay, brilliant. And Dawn, I guess I should give you the space to introduce yourself, and welcome back again, actually.
Thank you. Great to be here. My name is Dawn Nafus. I'm a principal engineer now in Intel Labs. I also run the Socio-Technical Systems Lab. And I also sit on Intel's Responsible AI Advisory Council, where we look after what kinds of machine learning tools and products do we want to put out the door.
Brilliant. Thank you, Dawn. And if you're new to this podcast, I mentioned my name was Chris Adams at the beginning of the podcast. I work at the Green Web Foundation. I'm the Director of Technology and Policy there. I'm one of the authors of a report all about the environmental impact of AI last year. So I have some background on this. I also work as the policy chair in the Green Software Foundation policy working group as well. So that's the other thing that I do. And we'll do our best to make sure that we link to every single paper and project on this. So if there are any particular things you found interesting, please do look for the show notes. Okay, Dawn, shall we start? I think you're both sitting comfortably, right? Shall I begin?
Yeah.
Okay, good. So Dawn, I'm really glad you actually had a chance to both work on this paper and share and let me know about it in the first place. And I can tell when I read through it, there was quite an effort to like do all the research for this. So can I ask, like, what was the motivation for doing this in the first place? And like, was there any particular people you feel really, really should read it?
Yeah, absolutely. We primarily wrote this for ourselves in a way. And I'll explain what I mean by that. So oddly, it actually started life in my role in responsible AI, where I had recently advocated that Intel should adopt a protect the environment principle alongside our suite of other responsible AI principles, right? Bias and inclusion, transparency, human oversight, all the rest of it. And so the first thing that comes up when you advocate for a principle, and they did actually implement it, is what are you going to do about it? And so we had a lot of conversation about exactly that. And really started to hone in on energy transparency, in part because, from a governance perspective, that's an easy thing to at least conceptualize, right? You can get a number. It's the place where people's heads first go to. And of course, it's the biggest part of, or a very large part of the problem in the first place, something that you can actually control at a development level. So, but once we started poking at it, it was, what do we actually mean by measuring and for what and for whom? So as an example, if we measured, say, the last training run, that'll give you a nice guesstimate for your next training run, but that's not a carbon footprint, right? A footprint is everything that you've done before that, which folks might not have kept track of, right? So, we're really starting to wrestle with this. And then in parallel, in labs, we were doing some socio-technical work on carbon awareness. And there too, we had to start with measuring, right? You had to start somewhere. And so that's exactly what the team did. And they found, interestingly, or painfully, depending on your point of view,
Yeah.
look, this stuff ain't so simple, right? If what you're doing is running a giant training run, you stick code carbon in or whatever it is, sure, you can get absolutely a reasonable number. If you're trying to do something a little bit more granular, a little bit trickier, it turns out you actually have to know what you're looking at inside a data center. And frankly, we didn't as machine learning people primarily. And so we hit a lot of barriers. And what we wanted to do was to say, okay, there are plenty of other people who are going to find the same stuff we did. So, and they shouldn't have to find out the hard way. So that was the motivation.
Well, I'm glad that you did, because this was actually the thing that we found as well when we were looking into this. It looks simple on the outside, and then it feels a bit like a kind of fractal of complexity. And there's various layers that you need to be thinking about. And this is one thing I really appreciated in the paper, that we actually, that was kind of broken out like that. So you at least have a model to think about it. And Charles, maybe this is actually one thing I can hand over to you, because I spoke about this kind of hierarchy of things you might do. Like there's stuff you might do at a data facility level, or right all the way down to a node level, for example. Can you take me through some of the ideas there? Because I know for people who haven't read the paper yet, that seemed to be one of the key ideas behind this, that there are different places where you might make an intervention. And this is actually a key thing to take away if you're trying to kind of interrogate this for the first time.
Yeah, I think it's both interventions and measurement, it's really more estimation at any level. And it also depends on your goals and perspective. So if you are operating a data center, right, you're probably concerned with the entire data center, right? Like the cooling systems, the idle power draw, the converting power to different levels, right? Like transformer efficiency, things like that. Maybe even the transmission line losses and all of these things. And you may not really care too much about like the code level, right? So the types of measurements you might take there or estimates you might make are going to be different. They're going to be at like the system level. Like, how much is my cooling system using in different conditions, different operating conditions, environmental conditions? From a user's perspective, you might care a lot more about like, how much energy, how much carbon is this job using? And that's going to depend on those data center variables. But there's also the degree of like, well, the data center is going to be running whether or not I run my job, right? So I really care about my job's impact more. And then I might be caring about much shorter term, more local estimates, like ones that might be from measuring the nodes that I'm running on's power, or which was what we did at NREL, or uh, much higher frequency but less accurate measurements that come from the hardware itself. Most modern computing hardware has a way to get these hardware estimates of the current power consumption, and you could log those. And there's also difficulties once you start doing that. Is the measurement itself can cause energy consumption, right? And also potentially uh, interfere with your software and cause it to run, more slowly and potentially use more energy. And so like there's difficulties there at that level. Um, yeah, but there's a whole suite of tools that are appropriate for different uses and purposes, right? Like measuring the power at the wall going into the data center may be useful at the data center or multiple data center level. Still doesn't tell you all the story, right? Like the losses in the transmission lines and where did that power come from are still not accounted for, right? Um, but it also doesn't give you a sense for like what happens when I take interventions at the user level. It's very hard to see that from that high level, right? Because there's many things running on the system, different conditions there. From the user's point of view, they might only care about like, this one key piece of my software that's running, like the kernel of this deep learning network. How much energy is that taking? How much additional energy is that taking? And that's like a very different thing that very different measurements are appropriate for, and interventions, right? Like changing that little, optimizing a little piece of code versus like maybe we need to change the way our cooling system works on the whole data center or the way that we schedule jobs. Yeah, and the paper goes through many of these levels of granularity.
Yeah, so this is one thing that really kind of struck out at me, because when it started at the kind of facility level, which is looking at an entire building, where you mentioned things like, say, power coming into the entire facility, and then I believe you went down to looking at, say, within that facility there might be one or more data centers. Then you're going down to things like a rack level, and then you're going down to a kind of either node level, and then you're even going all the way down to like a particularly tight loop, or the equivalent for that. And when you're looking at things like this, there are questions about like if you would make something particularly efficient at, say, the bottom level, the node level, that doesn't necessarily impact, it might not have an impact higher up, for example, because that capacity might be just reallocated to someone else. For example, it might just be that there's a certain kind of minimum amount of power draw that you aren't able to have much of an impact on. I mean, like these are some of the things I was surprised by, or not surprised by, but I really appreciated breaking some of these out, because one thing that was, I guess, counterintuitive when I was looking at this was that things you might do at one level can actually be can hinder steps further down, for example, and vice versa.
Yeah, that's right. I mean, I think two important sort of findings are, like battle scars that we got from doing these measurements. And one data set we produced is called Butter E, which is like a really large scale measurement of energy consumption of training and testing neural networks and how the architecture impacts it. And we were trying to get reasonable measurements while doing this. And one of the difficulties is in comparing measurements between runs on different systems, even if they're identically configured, can be tricky because different systems based on manufacturing variances, the heat, like how warm is that system at that time, anything that might be happening in the background or over the network, anything that might be just a little different about its environment can have real measurable impacts on the energy consumed. So like comparing energy consumption between runs on different nodes, even with identical configurations, we had to account for biases in there, like, oh, this node draws a little bit more power than this one at idle. And we have to like adjust for that in order to make a clear comparison of what the difference was. And this problem only gets bigger when you have different system configurations, or even same configuration, but running in like a totally different data center. So that was like one tricky finding. And I think two other little ones that I can mention, maybe we could go into more detail later, but another one, like you mentioned, is the overall system utilization and how that's impacted by a particular piece of software running, a particular job running, is going to vary a lot on what those other users of the system are doing and how that system is scheduled. So um, you can definitely get into situations where, yeah, I reduce my energy consumption, but that total system is just going to, that energy is going to be used some other time, especially if the energy consumption savings I get are from shortening the amount of time I'm using a resource and then someone else. But it does mean that the computing is being done more efficiently, right? Like if everyone does that, then more computing can be done within the same amount of energy. But it's hard to quantify that. Like, what is my impact? It's hard to say, right?
Well,
I see.
and,
Yeah.
and
And Dawn, go on. I can see you nodding.
yeah,
So
if
I
I
want
can,
you to come in now. Yeah.
yeah, if I could jump in a bit. I mean, I think that speaks to one of the things we're trying to bring out, maybe not literally, but make possible, is this, those things could actually be better aligned in a certain way, right? Like the energy that is, for example, when there is idle time, right? I mean, there are things that data center operators can do to reduce that, right? You can bring things into lower power states, all the rest of it, right? So in a way, kind of, getting, but at the same time, the developer can't control it, but if they don't actually know that that's going on, and it's just like, well, it's there anyway, there's nothing for me to do, right? That's also a problem, right? So in a way, you've got two different kinds of actors looking at it in very different perspectives. And the clearer we can get about roles, responsibilities, right, you can start to do things like reduce your power when things are idling. Yes, you do have that problem if somebody else is going to jump in. But Charles, I think as your work shows, there's still some idling going on, even though you
Oh yeah,
wouldn't
absolutely.
think. So maybe you could talk a little bit about that.
Yeah. So one really interesting thing that I didn't expect going into doing these measurements and this type of analysis was, um, well, first I thought, oh, great, we can just measure the power on each node, run things and compare them. And we ran into problems immediately, like you couldn't compare the energy consumption from two identically configured systems directly, especially if you were collecting a lot of data, because one is just going to use like slightly more than the other because of the different variables I mentioned. And then when you compare them, you're like, well, that run used way more energy, but it's not because of anything about how the job was configured. It's just that system used a little bit more. So if I switched them, I'd get the opposite result. So that was one thing. But then as we got into it and we were trying to figure out, okay, well, now that we've figured out a way to account for these variations, let's see what the impact is of running different software with different configurations, especially like neural networks with different configurations on the energy consumption. And our initial hypothesis was that it was based on mainly the size of the neural network and, like how many parameters, basically, like how many calculations, these sorts of things. And if you look in the research, a lot of the research out there about making neural networks and largely algorithms in general more efficient focuses on how many operations, how many flops does this take? And look, we reduced it by a huge amount. So that means that we get the same energy consumption reductions. We kind of thought that was probably true for the most part. But as we took measurements, we found that that had almost no connection to how much energy was consumed. And the reason was that the amount of energy consumed had way more to do with how much data was moved around on the computer. So how much data was loaded from the network, how much data was loaded from disk, how much data was loaded from disk into memory, into GPU RAM if we're using the GPU, into the different caching levels and even the registers. So if we computed like how much data got moved in and out of like level 2 cache on the CPU, we could see that that had a huge correlation, like almost direct correlation with energy consumption, not the number of calculations. Now, you could get in a situation where like basically no data is leaving cache and I'm doing a ton of computing on that data. In that case, probably number of calculations does matter. But in most cases, especially in deep learning, has almost no connection to the amount of data moved. So then we thought, okay, well, it's the amount of data moved, that the data, moving the data has a certain cost. But then we looked deeper and we saw that actually the amount of data moved is not really what's causing the energy to be consumed. It's the stalls while the system is waiting to load the data. It's waiting for the data to come from, system memory into level 3 cache. It needs to do some calculations on that data, so it's pulling it out. And while it's sitting there waiting, it's that idle power draw. it could be for like a millisecond or even a nanosecond or something, right? But it adds up. If you have, billions of accesses, each of those little stalls is drawing some power, and it adds up to be quite a significant amount of power. So we found that actually the driver of the energy consumption, the primary driver by far in what we were studying in deep learning was the idle power draw while waiting for data to move around the system. And this was like really surprising because we started with number of calculations. It turns out almost irrelevant, right? And then we're like, well, is it the amount of data moved around? It's actually not quite the amount of data moved around, but that does like cause the stalls whenever I need to access the data. But it's really that idle power draw. And I think that's probably true for a lot of software.
Yes, I think that does sound about right. I'm just going to try if I follow that, because there was I think there's a few quite key important ideas there. But there's also, if you aren't familiar with how computers are designed, it might. I'll try to paraphrase it. So we've had this idea that the main thing is like the number of calculations being done. That's like what we thought was the key idea. But
how much work,
Yeah, exactly. And what we know about is inside a computer, you have like multiple layers of, let's call them, say, caches, or multiple layers where you might store data. So it's easy and fast to access, but that starts quite small and then gets larger and larger, which is a little bit slower over time. So you might have, like you said, L2 cache, for example, and that's going to be smaller, much, much faster, but smaller than, say, the RAM on your system. And then if you go a bit further down, you've got like a disk, which is going to be way, way, way larger, and then that's going to be somewhat slower still. So moving between these stages so that you can process, that was actually one of the things that you were looking at. And then it turned out that actually the thing that, while that there is some correlation there, one of the key drivers actually is the chips kind of in a ready state, ready to actually waiting for that stuff to come in. They can't really be asleep because they know the data is going to have to come in, have to process it. They have to be almost like anticipating at all these levels. And that's one of the things that's one of the big drivers of actually the resource use and the energy use.
I mean, so like what we saw was we actually estimated how much energy it took like per byte to move data from like system RAM to level 3 cache to level 2 to level 1 to a register at each level. And at some cases, it was so small we couldn't even really estimate it. But in most cases, we were able to get an estimate for that. But a much larger cost was initiating the transfer. And even bigger than that was just the idle power draw during the time that the program executed and how long it executed for. And by combining those, we were able to estimate that most of that power consumption, like 99% in most cases, was from that idle time, even those little micro stalls waiting for the data to move around. And that's because moving the data, while it does take some energy, doesn't take that much in comparison to the amount of energy of like keeping the RAM on and the data is just like alive in the RAM, or keeping the CPU active, right? Like CPUs can go into lower power states, but generally at least part of that system has to shut down. So like doing it like at a very, very fine-grained scale is not really feasible. Many systems can change power state at a faster rate than you might imagine, but it's still a lot slower than like at a, per instruction per byte level of like, I need to load this data, like, okay, shut down the system and wait a second, right? Like not a second, like a few nanoseconds. It's just not practical to do that. And it's just keeping everything on during that time that's sucking up most of the power. So one strategy, simple strategy, but it's difficult to implement in some cases, is to initiate that load, that transfer earlier. So if you can prefetch the data into the higher levels of memory before you hit the stall where you're waiting to actually use it, you can probably significantly reduce this power consumption due to that idle wait. But it's difficult to figure out how to properly do that prefetching.
I see. Okay. So thanks, Charles. So it sounds like, okay, we might kind of approach this, and there might be some things which feel kind of intuitive, but it turns out there's quite a few counterintuitive things.
Yeah.
I'm Dawn, I can see you nodding away sagely here, and I suspect there's a few things that you might have to add on this, because this is, I mean, can I give you a bit of space, Dawn, to kind of talk about some of this too? Because I know that this is something that you shared with me before, is that, there are maybe some rules of thumb you might use, but it's never that simple, basically. You've realized that actually there's quite a bit more to it than that, for example.
Yeah, exactly. Well, I think what I really learned out of this effort is that measurement can actually recalibrate your rules of thumbs, right? So you don't actually have to be measuring all the time for all reasons, but even just that the simple, I mean, not so simple story that Charles told, it's like, okay, so I spend a lot of time talking with developers and trying to understand how they work. And at a developer perception level, right, what do they feel? Like what's palpable to them, right? They send the stuff off, have a cup of coffee, whatever it is, right? So they're not seeing all that, and when I talk to them, most of them aren't thinking about the kinds of things that were just raised, right? Like how much data are you looking at a time? You can actually set and tweak that. And that's the kind of, folks develop an idea about that and they don't think too hard about it usually, right? So with measuring, you can start to actually recalibrate the things you do see, right? I think this also gets back to, why is it counterintuitive that, some of these mechanisms and how you actually are training as opposed to how many flops you're doing, how many parameters. Why is that counterintuitive? Well, at a certain level, the number of flops do actually matter, right? If we do actually have a gigantic, I'm going to call myself a foundation model type size stuff, build out an entire data center for it. Yeah, it does matter. But as you get, down and down and down and more specific, it's a different ballgame. And there are these tricks of scale that are sort of throughout this stuff, right? Like the fact that, yes, you can make a credible claim that foundation model will always be more energy intensive than, something so small you can run on a laptop, right? That's always going to be true, right? No measurement necessary, right? You keep going down and down and you're like, okay, let's get more specific. You can get to actually where our frustration really started was if you try to go to the extreme, like try to chase every single electron through a data center, you're not going to do it, right? It feels like physics. It feels objective. It feels true. But at minimum, you start to hit the observer effect, right? That, which is what we did. We were, my colleague, Nicole Beckage, was trying to measure at an epoch level, right? Sort of essentially a round with, mini round of training. And what she found was that, she was trying to sample so often that she's pulling energy out of the processing and it messed up the numbers, right? So you can try to get down, into that, what feels like more accuracy. And then all of a sudden we're at a different ballpark. So these tricks of like aggregation and scale and what can you say credibly at what level, I think are fascinating. But you gotta get a feel for it in the same way that you can get a feel for, yep, if I'm sending my job off, I know I have at least, however many hours or however many days, right?
There's also so much variation that's out of your control, right? Like one run to another, one system to another, even different times where you ran on the same system can cause measurable and in some cases quite significant variations in the energy consumption. So it's more about, I think, about understanding what's causing the energy consumption. I think that's the more valuable thing to do. But it's easy to be like, I already understand it. And I think there's like a historical bias towards number of operations because in old computers without much caching or anything like this, right? Like I restore old computers and like an old 386 or IBM XT, right? Like it's running. It has registers in the CPU and then it has main memory. And almost everything is basically how many operations I'm doing is going to closely correlate with how fast the thing runs and probably how much energy it uses because most of the energy consumption on those systems is just basically constant no matter what I'm doing, right? It's just, it doesn't like idle down the processor while it's not working, right? And there's a historical bias that's built up over time that like was focused on the and it's also at the programmer level. Like I'm thinking about what is the computer doing?
What do I have control over? Yeah. What am I able to?
But it's only through actually measuring it that you gain a clearer picture of like what is actually using energy. And I think if you get that picture, then you'll gain an understanding more of how can I make this software or this data center or anything in between, like job allocation, more energy efficient. But it's only through actually measuring that we can get that clear picture. Because if we guess, especially using kind of our biases from how we learn to use computers, how we learn about how computers work, we're actually very likely to get an incorrect understanding, incorrect picture of what's driving the energy consumption. It's much less intuitive than people think.
Okay. There's a couple of things that I'd like to come in on, and then Dawn, I might give you a bit of space on this, because you said, so there's one, so we're just talking about like flops as a thing that people, are used to looking at, and like it's literally written into the AI Act, like things above a certain number of flops are considered, foundational models, for example. So, that's a really good example of what this actually might be. And I guess the other thing that I wanted to kind of like touch on is that I work in the kind of web land, and the Green Web Foundation is a clue in our organization's name. We've had exactly the same thing where we've been struggling to understand the impact of, say, moving data around and how much credence you should give to that versus things happening inside a browser, for example. It looks like you've got some similar kinds of issues and things to be wrestling with here. But Dawn, I wanted to give you a bit of space, because both of you alluded to this, about this idea of having an understanding of what you can and what you can't control, and how you might have a bias for doing one thing without and then miss something really much, much larger elsewhere, for example. Can I maybe give you a bit of space to talk about this idea of, okay, well, which things should you be focusing on, and also understanding of what's within your sphere of influence? What can you control? What can't you control, for example?
Yeah, exactly. I mean, I think it's, in a sense, you've captured the main point, which is, that measurements are most helpful when they are relevant to the thing you can control, right? So as a very simple example, there are plenty of AI developers who have a choice in what data centers they can use. There are plenty who don't, right? If when Charles worked at NREL, right? The supercomputer was there. That was it. You're not moving, right? So if you can move, that overall data center efficiency number, that really matters, because you can say, all right, I'm putting my stuff here and not there. If you can't move, like there's no need to mess with it. It is what it is, right? And this gets us into this interesting problem. Again, a tension between what you might look at it from a policy perspective versus what a developer might look at. We had a lot of kind of, they say come to Jesus. We had a little moment.
Yeah, we can. Been on a
podcast. I can. Yeah. Where there was this question of, are we giving people a bum steer by focusing at, granular developer level stuff, right? Where so much actually is on how you run the data center, right? So you talk about tricks of scale. On the one hand, the amount of energy that you might be directly saving just by, not using or not using, by the time all of those things move through the grid, and you're talking about energy coming off of the transmissions cables, right? In aggregate, might not actually be directly that big. It might be, but it might not be. And then you flip that around and you think about what aggregate demand looks like, and the fact that so much of AI demand is, that's what's putting pressure on our electricity grid.
Right now, yeah.
Right. Then that's the most effective thing you could do is actually get these, very specific individual jobs down and down and down. Right. So again, it's all about what you can control, but there are these, whatever perspective you take is just going to flip your understanding of the issue around.
So this was actually one thing I quite appreciated from the paper. There were a few things saying, and it does touch on this idea that, you might be focusing on the thing that you feel that you're able to control. But just because you're able to make a very, very efficient part of this spot here, that doesn't necessarily translate into a saving higher up in the system, simply because if higher up in the system it isn't set to actually take advantage of that, then you might never achieve some of these savings. It's a little bit like when you're working in cloud, for example. People tell you, do all these things to kind of optimize your cloud savings. But if people are not turning data centers off, at best, you might be slowing the growth of infrastructure rollout in future. And these are much, much harder things to kind of claim responsibility for, or say that, yeah, it was definitely, if it weren't for me doing those things, we wouldn't have had that happen. This is one of the things that I appreciated the paper just making some allusions to and saying, look, yeah, this is, you know, this is why, I mean, to be honest, when I was reading this, I was like, wow, there was obviously some stuff for beginners, but there's actually quite a lot here, which is quite meaty for people who are thinking at this at a much larger systemic level. So there's definitely things like experts could take away from this as well. So I just want to check, are there any particular takeaways the two of you would like to kind of draw people's attention to beyond what we've been discussing so far? Because I quite enjoyed the paper and there's a few kind of nice ideas from this. Charles, if I just give you a bit of space to kind of come in.
Yeah. I've got kind of two topics that I think build on what we've talked about before, but could be really useful for people to be aware of. So one is sort of one of the outcomes of our studying of the impact of different architectures, data sets, hyperparameter settings on deep neural network energy consumption was that the most efficient networks, most energy efficient networks, and largely that correlates with most time efficient as well, but not always. The most efficient ones were not the smallest ones, and they were not the biggest ones, right? The biggest ones were just required so much data movement. They were slow. The smallest ones, they took a lot more iterations, right? It took a lot more for them to learn the same thing. And the most efficient ones were the ones where the working sets, where the amount of data that was moved around matched the different cache sizes. So as you made the network bigger, it got more efficient because it learned faster. But then when it got so big that the data in like between layers, the communication between layers, for example, started to spill out of a cache level, then it became much less energy efficient because of that data movement stall happening. So we found that like there is like an optimum point there. And for most algorithms, this is probably true, where if the working set is sized appropriately for the memory hierarchy, you gain the most efficiency, right? Because generally, like as I can use more data at a time, I can get my software to work better, right? More efficiently. But there's a point where it falls out of the cache and that becomes less efficient. Exactly what point is going to depend on the software. But I think focusing on that working set size and how it matches to the hardware is a really key piece for almost anyone looking to optimize software for energy efficiency, is to think about that. How much data am I moving around and how does that map to the cache? So that's like a practical thing.
Can I stop you there? Because that, I find that quite interesting in that a lot of the time as developers, we're kind of taught to kind of abstract away from the underlying hardware. And that seems to be going the other way. That's saying, no, you do need to be thinking about this. You can't.
It makes a massive difference, right? And so like for neural networks, that could mean sizing my layers so that those working sets match the cache hierarchy, which is something that no one even considers. It's not even close in most architectures. Like no one has even thought about this. The other thing is on your point about data center operations and kind of the different perspectives. One thing that we started to think about as we were doing some of this work was it might make sense to allocate time, or in the case of like commercial data center, commercial cloud operator, even like charge field, based on at least partly the energy rather than the time, to incentivize them to use less energy, right? Like make things more energy efficient. Those can be correlated, but not always, right? And another piece of it that I wanted to touch on of that same puzzle is from a lot of data center operators' perspective, they want to show their systems fully utilized, right? Like there's demand for this system, so we should build an even bigger system and a better system. When it comes to energy consumption, that's probably not the best way to go, because that means that those systems are sitting there probably doing inefficient things, maybe even idling a lot of time, right? Like a user allocated the node, but it's just sitting there doing nothing, right? It may be more useful, instead of thinking about like how much is the system always being utilized, but think about how much computation or how many jobs or whatever your like utilization metric is, do I get like per unit energy, right? And you may think about how much or per unit carbon, right? And you may also think about like how much energy savings can I get by doing things like shutting down nodes when they're unlikely to be utilized, and more about like having a dynamic capacity, right? Like full tilt, I can do however many flops or whatever, right? But I can also scale that down to reduce my idle power draw by 50% in low demand conditions, And if you have that dynamic capacity, you may actually be able to get even more throughput, but it's with less energy because when there's no demand, I'm like scaling down my data center, right? And then when there's demand, I'm scaling it up. But these are things that are require cultural changes in data center
Okay.
operations to happen.
I'm glad you mentioned this thing here because Don, I know that you had some notes about. It sounds like in order for you to do that, you probably need different metrics exposed or different kinds of transparency to what we have right now. Probably more actually. Dawn, can I give you a bit of space to talk about this? Because this is one thing that you told me about before, and it's something that is actually touched on in the paper quite a few times actually.
Yeah, I mean, I think we can notice a real gap in a way between the kinds of things that Charles brings his attention to and the kinds of things that show up in policy environments and responsible AI circles, right? Where I'm a bit closer, we can be a bit vague. And I think we are at the stage where, at least my read on the situation is that, there's, regardless of where you sit in the debates, and there are rip-roaring debates about what to do about the AI energy situation. But I think transparency is probably the one thing we can get the most consensus on. But then, just back to that, what the heck does that mean? And I think we need a little, more beats than are currently given to actually what work are those measurements doing? Some of the feedback we've gotten is, well, can't you just come up with a standard? What's the right standard? It's well, no, actually, if data centers aren't standard, and there are many, many different ways to build a model, then yes, you can have a standard as a way of having a conversation across a number of different parties to do a very specific thing, right? For example, Charles's example, suggested that if we're charging on a per energy basis, that changes a whole lot, right? But what you can't do is to say, this is the standard that is the right way to do it, and then that meets the requirement, because that's what we found is that clearly the world is far more complicated and specific than that. So I would really encourage the responsible AI community to start to get very specific very quickly, which I don't yet see happening, but I think it's just on the horizon.
Okay, well, I'm glad you mentioned about maybe taking this a little bit wider, because we've spent a lot of time talking about this paper, but there's other things happening in the world of AI actually. And I want to give you folks a bit of space to kind of talk about anything that things that you would like to kind of direct some attention to, or you've seen that really you found particularly interesting. Charles, can I give you some space first and then give Dawn the same to
Sure.
I don't know, either shout out or point to some particular things that if they found this conversation interesting so far, what they might want to be looking at?
Yeah, I mean, I think both in computer programming, computer science at large, and especially in machine learning, we've kind of had an attitude, especially within deep learning, within machine learning, an attitude of throwing more compute at the problem, right? And more data. The more data that we put through a model and the more complicated the model is, the more capable it can be. But this brute force approach is one of the main things that's driving this increasing computing energy consumption, right? And I think that it is high time that we start taking a look at making the algorithms we use more energy efficient instead of just throwing more compute at it. It's easy to throw more compute at it, which is why it's been done. And also because there hasn't been a significant material incremental cost of now we need twice as many GPUs. No big deal. But now we're starting to hit constraints because we haven't thought about that incremental energy costs. We haven't had to as an industry at large, right? But now it's starting to be well, we can't build that data center because we can't get the energy to it that we need to do the things we want to do with it, because we haven't taken that incremental cost into account over time. We just kind of ignored it, and now we hit the barrier, right? and so I think thinking about the energy costs, and probably this means investing in finding more efficient algorithms, more efficient approaches, as well as more efficient ways to run data centers and run jobs. That's going to become increasingly important, even as our compute capacity continues to increase. The energy costs are likely to increase along with that as we use more and more, and we need to create more generation capacity, right? It's expensive at some point. We're really driving that energy production. And that's going to be increasingly an important cost, as well as it is now, like starting to be a constraint to what kind of computing we can do. So I think investing in more efficient approaches is going to be really key in the future.
So there's one thing that I think Dawn might come in on this actually, is that you're talking about, I mean, it seems that you're talking about having more of a focus on surfacing some of the kind of efficiency, or the fact that resource efficiency is actually going to be something that we probably need to value or sharpen. I mean, because as I understand it so far, it's not particularly visible in benchmarks or anything like that right now. Like, and if you have benchmarks deciding what counts as a good model or a good use of this, until that's included, you're not going to have anything like this. Is that the kind of stuff you're kind of suggesting we should probably have, like some more recognition of, like, or even like you're taking at the energy efficiency of something and being that thing that you draw attention to or you include in counting something as good or not, essentially.
You know, I have a particular view of efficiency. I suspect many of your listeners might as well. I think it's notable that at the moment where we're seeing that, the model of the month, apparently, or the set of models, DeepSeek has come onto the scene, and immediately we're starting to see, for the first time, Jevons paradox showing up in the public discourse. This is the paradox that when you make things more efficient, you can also end up stimulating so much demand.
Yeah, absolute use grows, even though it gets individually more efficient.
Yeah, exactly. Again, this is like this topsy-turvy world that we're in. And so, now the Jevons paradox is front page news. My view is that, yes, again, we need to be particular about what sorts of efficiencies are we looking for where, and not, sort of willy-nilly, create an environment where, which I'm not saying you're doing, Charles, but, what we don't want to do is create an environment where if you can just say it's more efficient, then somehow, we're all good, right? Which is, what some of the social science of Energy Star has actually suggested, that that stuff is going on. With that said, right, I am a big fan of the Hugging Face Energy Star initiative. That looks incredibly promising. And I think one of the things that's really promising about it, so this is, leaderboards when, people put their models up on Hugging Face. There's some energy measurement that happens, some carbon measurement, and then, leaderboards are created and all the rest of it. And I think one of the things that's really good at, right? I can imagine issues as well, but you're creating a way to give some people credit for actually looking. B, you're creating a way of distinguishing between two models very clearly, right? So in that context, do you have to be perfect about how many kilowatts or watts or whatever it is? No, actually, right? You're looking at more or less in comparable models. But C, it also interjects this kind of path dependence. Like, who is the next person who uses it, right? That really matters. If you're setting up something early on, yes, they'll do something a little bit different. They might not just run inference on it. But you're changing how models evolve over time and kind of steering it towards even, having energy presence at all. So that's pretty cool to my mind. So I'm looking forward to
Cool. We'll share a link to the Hugging Face. I think, do you know what they were called? I think it's it was initially called the Energy Star Alliance, and then I think they've been told that they need to change the name to the Energy Score Alliance from this, because I think Energy Star turned out to be a trademark. But we can definitely add a link to that in the show notes, because this actually I think it's something that is officially visible now. It's something that people have been working on late last year, and now there is. We will share a link to the actual GitHub repo, to the code on GitHub to kind of run this, because this works for both closed source models and open source models. So it does give some of that visibility. Also in France, there is the Frugal LLM challenge, which is also sounds similar to what you're talking about. This idea of essentially trying to emphasize more than just the pay a bit more attention to the energy efficiency aspect of this. And I'm glad you mentioned the DeepSeek thing as well, because suddenly everyone in the world is an armchair expert on William Stanley Jevons paradox stuff.
Yeah, everybody knows. It's great.
Yeah.
Actually, Chris, if I could just add one small thing, which since you mentioned the Frugal effort in France.
Yeah.
There's a whole computer science community, sort of almost at a step's length from the AI development community, that's really into just saying, look, what is the purpose of the thing that I'm building, period. And even and that, frugal computing within limits, all of that world is really about how do we get, just something that somebody's going to actually value, as opposed to, getting to the next, score on a benchmark leaderboard somewhere. So I think that's kind of also lurking in the background here. And
I'm glad you mentioned this. What we'll do, we'll add links to both of those. And you immediately make me think of, there's this actual, so we're technologists mostly, the three of us. We're talking about this, and I work in a civil society organization. And just this week, there was a big announcement, like a kind of set of demands from civil society about AI that's actually being kind of shared at the AI Action Summit, this big summit where all the great and good are meeting in Paris, as you alluded to, next week to talk about what should we do about this. And it's literally called Within Bounds, and we'll share a link to that. And it does talk about this, like, well, if we're going to be using things like AI, we need to have a discussion about what they're for. And that's the first thing I've seen, which actually has discussions about saying, well, we should be actually having some concrete limits on the amount of energy for this, because we've seen that if this is a constraint, it doesn't stop engineers, it doesn't stop innovation. People are able to build new things. What we should also do is we should share a link to, I believe, Vlad Koraoma. We did an interview with him all about Jevons paradox late last year. And that's a really nice deep dive for people who want to basically sound knowledgeable in these conversations on LinkedIn or social media right now. It's a really useful one there as well. Okay, so we spoke a little bit about these ones here. Charles, are there any particular projects you'd like to kind of like name check before we start to wrap up? Because I think we're coming up to the hour now, actually.
I don't know, not particular, but I did mention earlier, we published this Butter E data set and a paper along with it, as well as a larger one without energy measurements called Butter. Those are available online. You can just search for it and you'll find it right away. I think if that's of interest to anyone hearing this, there's a lot of measurements and analysis in there, including, all the details of analysis that I mentioned, where we had this journey from number of compute cycles to like amount of stall in terms of what drives energy consumption.
Oh, it's visible so people can see it. Oh, that's really, really cool. I didn't realize about that. Also, while you're still here, Charles, while I have access to you, before we did this interview, you mentioned there's a whole discussion about wind turbines killing birds. And you were telling me this awesome story about how you were able to model the path of golden eagles to essentially avoid these kind of bird strike stuff happening. Is that in the public domain? Can we link to that?
There's several papers. I'll have to dig up the links, but there's several papers we published and some software also to create these models. But I worked on a project where we looked at, we took eagle biologists and computational fluid dynamics experts and machine learning experts, and we got together and we created some models based off of real data, real telemetry of tracking golden eagle flight paths through, in many locations, including at wind sites, and match that up with the atmospheric conditions, the flow field, like orographic updrafts, which is where the wind hits, like a mountain or a hill, and some of it blows up, right? And golden eagles take advantage of this, as well as thermal updrafts caused by heating at the ground, right, causing the air to rise to fly. Golden eagles don't really like flapping; they like gliding, and because of that, golden eagles and other soaring birds, their flight paths are fairly easy to predict, right? Like you may not know, like, are they going to take a left turn here or a right turn there? But generally, they're going to fly in the places where there's strong updrafts. And using actual data and knowledge from the eagle biologists and simulations of the flow patterns, we were able to create a model that allows wind turbines to be sited and also operated, right? Like under what conditions, like what wind conditions in particular, and what time of year, which also affects the eagle's behavior. Should I perhaps reduce my usage of certain turbines to reduce bird strikes? And in fact, we showed that it could be done without significantly or even at all impacting the energy production of a wind site. you could significantly reduce the chances of colliding with a bird.
And it's probably good for the birds too, as well.
Absolutely. Yeah.
All right, we definitely need to find some links to that. That's going to be absolute catnip for the nerdy listeners who are into this. Dawn, can I just give you the last word? Are there any particular things that you'd like to? I mean, actually, I should ask. We'll add links to you and Charles online. But if there's anything that you would draw people's attention to before we wrap up, what would you pay? What would you plug? Yeah.
I actually did want to just give a shout out to National Renewable Energy Lab, period. One of the things that are amazing about them, speaking of eagles, a different eagle, is they have a supercomputer called Eagle. I believe they've got another one now. It is lovingly instrumented with all sorts of energy measurements. Basically anything you can think to measure, I think you can do it in there. There's another data set from another one of our co-authors, Hilary Egan, that has sort of jobs data. You can dig in and explore what a real world data center job situation looks like. So I just want to give all the credit in the world to National Renewable Energy Lab and the stuff they do on the computing side. It's just phenomenal.
Yes, I think that's a really, I would echo that very much. I'm a big fan of NREL and the output for them. It's really like a national treasure. Folks, I'm really, thank you so much for taking me through all of this work and diving in as deeply as we did, and referring to things that soar as well, actually, Charles. I hope we could do this again sometime soon, but otherwise, have a lovely day, and thank you once again for joining us. Lovely seeing you two again.
Good seeing you.
Okay, ciao. Hey everyone, thanks for listening. Just a reminder to follow Environment Variables on Apple Podcasts, Spotify, or wherever you get your podcasts. And please do leave a rating and review if you like what we're doing. It helps other people discover the show. And of course, we'd love to have more listeners. To find out more about the Green Software Foundation, please visit greensoftware.foundation. That's greensoftware.foundation in any browser. Thanks again, and see you in the next episode.